Here we have a problem that specifies that all the surfaces are frictionless. And the question is asking us, what is acceleration of block B and block A? So everything is frictionless. That's the main thing that we gotta take note of in this case. And in this case, I'll be doing the problem with respect to a person looking at this whole system from the ground. So frame of reference with respect to ground. I'll talk about why I'm choosing my ground as the reference later on. But for now, just keep in mind that I'm taking everything in reference of the ground. I will set up my coordinate system, just a regular X and Y coordinate system, positive here, Y positive going up. Now, let's try to understand how the system is going to behave. So we know for sure that the block B is going to be moving down like this. And so if block B moves down like that, because there is no friction on this ground over here, block A will move to the left. So when a block A moves to the left, it has some acceleration, and I'm going to call that acceleration A of A. Now when a block B moves down the incline, what we see is it going down like this, right? Now this acceleration is not the acceleration of block B. It is actually the acceleration of block B with respect to A. Imagine a person sitting on top of block A, right? Sitting on top of block A. And if the person is moving along with the block A, then this person sees this acceleration. The person sitting at the ground reference, does not see this. The person sitting at the ground reference would see something like this. So acceleration of block A is going like this. Acceleration of B with respect to A is going like this. And so then the acceleration of block B would look something like that. So this is what this person sees. The person that is sitting on block A, who's moving along with block A, who's accelerating with block A, would see A of B with respect to A. And it actually kind of makes sense because as block B is moving down the incline, right, as block B is moving down the incline, it has some x acceleration or acceleration in the x direction. But at the same time, block A is going in this direction. So in the x, we see that because they kind of cancel each other out, the acceleration of block B turns out to be a little less to the right, right? The x component of AB is less than the x component of A of B with respect to A. So hopefully that kind of makes sense in terms of relativity. Now, let's try to get more in depth of why we're looking everything in respect with the ground. Now, you might be thinking, oh, if I can just put a person on top of block A and I can just look from this guy's perspective, then why don't I just use that? Now, that is what I used to think as well. But one of the main fundamental concepts of Newton's law, right? Newton's law, which is basically like pretty much what we use to solve any kind of classical mechanics problem, right? So Newton's law only work on inertial frame of reference. So what does it mean to be an inertial frame of reference? This means that our frame is not moving, or if moving, it is moving at a constant velocity. constant velocity. So this is what an inertial frame of reference is. Now let's look at the guy at the ground. Is he moving at all? Absolutely not, right? He's not moving at all. This person is just stuck to the ground and he's just looking at this, whatever the system is over here. He's just looking at it from his point of reference, which is the ground. And Newton's law only works on inertial frame of reference. Another frame of reference is the non-inertial frame of reference, right? Frame of reference, which is a frame that is moving. That is moving at a non-uniform velocity, or non-uniform velocity, or basically accelerating. So what would be a non-inertial frame of reference in this case? Well, the non-inertial frame of reference in this case would be a person sitting on block A. A person that is sitting on block A would also be accelerating at the same acceleration that block A accelerates at, right? So we cannot use Newton's law in those kind of cases. So that is why I chose ground reference. The whole point of having to do relativity is because I want to make sure that my Newton's law actually apply everywhere that I want to, right? Now that we have that, let's get a little more deep into this relativity right here. So if I just look at the vectors right here, if I take this vector and I add this vector, so if I take acceleration of A and add it with acceleration of B with respect to A, I end up getting acceleration of B, right? This is the simple vector addition. You have starting at the end point, going to the front point, end point to the front point, and we have this end point to the front point. Simple vector addition. So from this, so keep note of something. Every time I wrote acceleration in this case, I always put a arrow at the top where I'm trying to signify that our acceleration is a vector component, right? Vector component, meaning it has both magnitude and direction, right? So I'm really trying to focus on that point that these are vector components. And now let's see how they come into play. Well, which way is acceleration of A pointing? My coordinate system is like this, where right is positive and up is positive. Well, acceleration of A is pointing to the left. So it's going to be negative A of A, I hat denoting in the x direction, but it's negative, so I put a minus sign. Now let's see, acceleration of B with respect to A, right? Acceleration of B with respect to A is parallel to the incline. And I know the angle, this is theta. So that means I can basically get the vector components of this. So I have acceleration of B with respect to A. I know this is theta with the horizontal. So that means I can get the vector components like this. So then this will simple trig A of B with respect to A sine theta. But this is going to be negative because it's pointing down. This will be A of B with respect to A cosine theta. This is positive because it's pointing to the right. Okay. So once we have that, we will write the vector components of A of B with respect to A. So let's see, if we write the vector components, I have A of B with respect to A cosine theta in the positive I hat direction, then plus negative A of B with respect to A sine theta j hat direction. And this equals A of B, right? So A of B has a X component and a Y component, which makes sense, right? That is what we would see as a person that is sitting at the ground. That is what we expect, the block to move to the right and move down. So if I put this in a proper manner, I get A of B equals, I put the I hat components together, A of B of A cosine theta minus A of A. Oh, I should get rid of the vector sign here because I already took care of the direction and the magnitude, so no vector sign there. So this in the I hat, and then plus negative A of B with respect to A sine of theta, and this in the J hat direction, right? So thing to take notice of, acceleration of block B, right? Acceleration of block B has both X and Y components, okay? And they intuitively make sense because we know that block B should be moving to the right and going down, right? So they intuitively make sense. So now we have gone through ground reference, relativity, Newton's law in inertial frame of reference, non-inertial frame of reference. Now this has basically become a simple classical mechanics problem. And with pretty much all problems that require forces, what we must do is we must draw the free body diagram. So let's draw the free body diagram for both block A and B separately. This is block A. So we have the weight of block A, which is MAG, right? Weight is just mass times gravity. And because block A is in contact with the ground, which is frictionless, we only have a normal force. Now, as we see here, block A and B are in contact with each other, right? So that means they're going to be reacting to each other. So we have a force R. I'm going to call it R. So this is reaction force from block B onto block A. So this is block B acting on block A. Now, because of Newton's third law, we should know that block A is going to act the same magnitude but opposite to block B, right? So Newton's third law tells us that every action has equal and opposite reaction. So that's the same thing going on here. If block B is acting on block A, that means block A has to act on block B. So equal, that is why I'm calling this one R as well. They're equal and they're opposite. So that is why I drew the direction opposite. Here I've drawn it going down and left. Here I've drawn it going right and up. Now just to make clear, I'll write this as reaction force from block A onto block B. Okay, and let us not forget the weight of block B and GB. And that pretty much gives us the free body diagram. Now let's look at the angle of, again, I'm going to draw my coordinate system just to keep reminding that I'm taking a regular coordinate system, just a simple X and Y. So that means I have to break down this R into components, right? So I have to break it down into components. So let's look at this. If this is theta, then this has to be theta. Now, one thing to notice is this R force, right? The reaction force from block A onto block B, or block B onto block A, it is acting perpendicular to the surface, right? That's something that we need to, it's acting perpendicular to the surface. Okay. So if this is theta, then this is theta, then this will be 90 minus theta, then this will be theta. Okay. So that's just like basic geometry and a little bit of trick, I guess. But hopefully that makes sense. I'm going to erase this just to make it a little more clear. Oh, erased way too much. Okay, so we have theta over there. Let's look at block B. So block B, if this is theta, then this is 90 minus theta, because this is basically, I'm basically making an imaginary right angle triangle here, right? And if this is 90 minus theta, then this has to be theta. So same thing, basic geometry, a little bit of trig and stuff. So let me, just to make it clear, I'm gonna make this a little clean, erase some of the stuff. Okay. Now, what do? After we have this, we basically write summation of forces in the fx, right? So how about we do this? So this is for block B. So this is for block B. For block A, summation of fx gives me negative r of sine theta equals m negative a of a, right? So if I look at the components, let me actually draw it out. So my r vector points like this, my r force point like this, right? But since my coordinate system is in the regular coordinate system, I want to break it down into components. And so when I break it down into components, I basically get negative r sine theta here and negative r cosine theta here. And we know that this block is accelerating in the x direction, right? But it's accelerating in the negative x direction, like we drew here. It's accelerating in the negative x direction, right? So that's why I put a negative a of a. Now I can also do summation of fy. So n minus r of cosine theta, right? Minus r of cosine theta minus mag equals 0. Because in the y direction, this block is not moving, right? This block is not moving in the y direction. Okay, so that is for that is pretty much all that we need for block A. Let's look at block B. Now this will be a little tricky. Let me just bring this back. So let me just, oh, my pen is not working, but let's see. Let me copy this and let me paste it over here. So acceleration of block B, right, is a vector, and in component form, it is going in the x direction and also in the y direction, which intuitively makes sense like we talked about before. So let's look at this now. So if I do summation of fx, what do I get? Let me actually draw the r vector, the r force again. So I have something like this. This is theta over here. So then this would be r of sine theta, right? And then this would be r of cosine theta. And both are positive because it's going to the right and it's going up. So if I do summation of fx, what do I get? I get r of sine theta equals m of block B, right? And what is the acceleration in the x direction? Well, in the x direction, it's this right here, right? The x component. It's the x component. So that is why my acceleration will be b with respect to a cosine theta minus a of a. Okay, so because this is in the x direction, right? This is summation of force in the x direction. Well, then we need the acceleration in the x direction, and the acceleration in the x direction is this component right here. Now doing the similar thing in summation of fy, let's see what we get. We get r of cosine theta going up minus mbg equals negative a of b with respect to a sine theta, right? Because we want the acceleration in the y direction, which is right here. So this goes right here, and this goes right here. One thing I forgot to do, this should be mass of A, not just m, because there are two different blocks, just got to specify that. Okay, so let's see. We want to find acceleration of A and acceleration of B. Now let's see, we have one equation, two equation, three equation, four equation. And let's see how many unknowns we have. N is an unknown. Acceleration of A is an unknown. R is an unknown. So that's three unknowns, and A of B with respect to A is unknown. Okay. By the way, I'm doing all of this in a symbolic form, but we're gonna assume these parameters are given. So I'm basically assuming that mass of A will be given, mass of B will be given, and theta will be given, right? The angle of the incline will be given. So all of this will be given. So my unknowns are basically R, right? One more time. My unknown is R, acceleration of A, my normal force, and acceleration of B with respect to A. Everything else is known. I have four unknowns, four equations. That means we should be able to solve this. Now, honestly, at this point, it is all algebra, and it just depends on how you like to do it. I'm going to do it my way. It might not even be the most efficient way to do it, to be honest, but I'm just going to give it my best shot. Okay, so one thing I'll just say you right off the top, I don't want to deal with this Fy, because I just want AY, acceleration of A and acceleration of B. It does not come in equation 2 anywhere. So I don't really need this. I'm not even going to look at that. Unless the question asks you to find n, we don't really care about the equation for now. Okay. But let's look at equation 1. If I look at equation 1, I get negative r of sine theta equals negative m of A, acceleration of A. Negative, negative cancels. And then I can say r equals m of A, acceleration of A, sine theta. Okay, so I have r in terms of acceleration of A. All right, now let's look at equation 4. Equation 4, what do we have? We have r cosine theta minus mbg equals negative A of B with respect to A sine of theta. Right? Now, I'm just going to move things around to make it positive. So I'm just moving things around. What did I forget? Sorry guys. I forgot to put a mass of B here, because the summation of force equals mass times acceleration, not just acceleration, right? So this should be negative m of B, A of B with respect to A sine theta. So mb A of B with respect to A sine theta. Okay? So that's my equation 1, that's my equation 4. That is what I'm getting from equation 4. And now I'm going to look at equation 3. From equation 3, I get r of sine theta equals mb A of B with respect to A cosine theta minus m of B acceleration of A. Now I'm gonna do some weird stuff. It just depends how you want to do your algebra, right? I just feel comfortable doing it this way. So m of B, A of B with respect to A cosine theta equals r sine theta plus m of b, a with respect to a. Okay, so that is what I get now. So let's do a little bit of algebra here. I'm going to multiply this equation over here. Let me just do it in different color. So this equation, I'm going to multiply it by cosine theta over sine theta. Okay, now this is my way of doing algebra. Might not be the most efficient, but let's see what we get. mgb cos theta over sine theta minus r cosine squared theta over sine theta equals mb a of b with respect to b cos theta. Okay. Now, the whole trick behind this is the same as this. R is R, right? So what I'm doing is I'm basically substitute and substitute. So let's see what I get here when I substitute them. mbg of cosine theta over sine theta minus r of cosine squared theta over sine theta equals, actually, I'm not going to substitute the r yet, plus m of b a of a. Okay, so actually let me just remove this to make it more clear. So first I substituted this because they're the same thing, right? Now I'm going to substitute r into this and into this. So substitute. So when I substitute r, let's see what we get. mbg cos theta over sine theta minus r is m of a of a over sine theta and cosine squared theta sine theta equals m of a of a sine theta plus m of b a of a. Sine theta cancels out and everything else remains the same. So the whole premise of me doing all that stuff, right, all that stuff, is to just make sure that I'm able to solve for something. So in this case, look at this equation. My only unknown in this k is acceleration of a. That is my only unknown. Everything else I know, right? Because I'm saying theta will be given to me, m of b will be given to me, m of a will be given to me, and we know gravity is just a constant g. So my only unknown is a of a. So I can find an equation for a of a in respect to everything else. Again, a lot of algebra, but that's just how classical mechanics are. And working with numbers would definitely be easier, I guess. But there's like some kind of beauty of just working with just like pure variables. Because at the end, when you get a equation, it feels very satisfying. Well, at least for me. Okay, so I'm gonna do some basic algebra here. So m of a of a plus m of b a of a. So I'm gonna move this to the other side. So m of a of a cosine squared theta sine squared theta. Okay, let's see, what more can we do? So I'm gonna multiply this whole thing by sine square. No, let's not do that. That would just make my life even more hard. Let's see. Okay. mbg cosine theta over sine theta. So the left side, I still leave it as the same. But now on the right side, I'm going to take the LCM. Right? I'm taking the LCM in this case. A of a sine squared theta plus m of a of a cosine squared theta. All of this divided by sine squared theta. So I basically took the LCM, like the common of everything, right? Now let's focus on two main things. Let's focus on this, and let's focus on this. So m of a of a, sine squared theta, plus m of a of a, cosine squared theta. So I'm only focusing on those to prove a point, basically. M of a of a common, sine squared theta plus cosine squared theta. What is sine squared theta plus cosine squared theta? Well, just from basic trig, we know that sine squared theta plus cosine squared theta is 1. So this is m of a of a. Okay? So all of this is to just prove that point. I'm just going to place it on the side, just so we don't forget. And now m of bg cosine theta over sine theta equals m of a plus m of b of a sine squared theta, all of this divided by sine squared theta. I have sine theta on the bottom here, sine squared theta on the bottom here. So I can cancel this, I can cancel this, 1 remains, right? So mgb, so I'm going to move this sine over this way because 1 remains here, right? 1 remains. So sine theta cosine theta equals, I'm going to take acceleration of a common from both of these, and I get m of a plus m of b sine squared theta. So the final equation I get is this right here. Oh, let's see. So m of a plus m of b sine squared theta. And like I said, when working with just variables, I think when you get the final equation, it usually is pretty satisfying, and usually it turns out to be quite beautiful. Let's see. So that is acceleration of a. Basically did a bunch of algebra. Probably bored you guys, to be honest. So just not to bore you guys, I'm going to solve for a of b with respect to a. Well, not solve for it. I'll just basically tell you what I would get. M of a plus m of b g sine of theta, and m of a plus m of b sine squared theta. So these are the two equations that I would basically get, right? So I would get this for a of a, and I'll get this for a of, oh, that didn't work out, a of b with respect to a. So that is what I'll basically get. Okay, this one didn't work out either. Let me just, okay, there we go. So I have a of a and a of b with respect to a. So if I want to find a of b, right, a of b was given by what? Let me just bring that down one more time. Right here. So a of b was given by this. Copy. Paste. So a of b was given in vector form like this. If I want to find the, so I can find the vector form, that's easy. But if I want to find the magnitude of a of b, I basically take the square of the x component and then the square of the y component, and that would give me the magnitude of a of b, right? And that is pretty much the solved version, or fully solved equations for this problem. Okay, so hopefully you guys were able to gain something out of this. Main thing to remember, ground frame of reference, Newton's law only works in the inertial frame of reference. A little bit of vector, a little bit of relative acceleration here, and the rest of it is just simple classical mechanics stuff, right? Drawing free body diagram, getting the angle the force is at, doing all the summation of fx, summation of fy, yeah, all that good stuff. All right.